Hello, we will explain our paper about LVCMOS based design of energy efficient RAM on FPGA. And about the content of the paper, we have abstract, introduction, related work research, implementation and results, conclusion, as well as future scope. Before I move on further, there are two keywords which must be explained. One is the LVCMOS and other is FPGA. LVCMOS stands for low voltage complementary metal oxide semiconductor. As the name suggests, it's a low voltage class of digital integrated circuits. We could have used CMOS, instead we are using this LVCMOS because the main focus here is power and not much of the voltage is required for the RAM. So we are trying to reduce power usage or say consumption or power cost. So LVCMOS is a way to go. And about the FPGA, these are field programmable gate arrays. They're actually semiconductor device based around a matrix of CLBs. These are actually specialized ICs and can be programmed or reprogrammed according to the application or functionality required. So back to the content, we first have abstract. That is the basis of our paper which tells about our research work. So we have used Xilinx ISC 14.7 version to test and obtain our results, and the hardware language that have been used is Verilog. We have implemented our RAM on FPGA using LVCMOS 15 and LVCMOS 25, that is at 1.5 volts and 2.5 volts. We are now calculating total power consumption, that is actually combinational power consumption of like logic power, signal power loss, input output power, and etc., so that we can try to minimize it at different temperature and at different parameters like change in capacitance to get the value which can be used to make energy efficient RAM. Getting started with RAM, or say random access memory, used to store and retrieve temporary data which is required frequently by our machine. It's faster than any hard disk or long-term storage devices. Actually, speed is one of the factors for a good RAM, but we don't want the machine our RAM is deployed in eat too much power. So here we do the power analysis and we are testing thermal stability as well at extreme temperatures. Here is the schematic figure of RAM, where it's clearly visible that we have 4 inputs and 1 output. Input address as A, data inputs as DI, clock as CLK, to determine how fast it can run and process data. Also, we have kept our clock period cycle as 1 nanosecond or 1 gigahertz device operating frequency. There is WE also, which stands for write enable. If it's 0, the RAM does the read function, and when it's 1, the RAM does the write function. A RAM uses 2.209 nanoseconds for input processing and 5.259 nanoseconds for overall output processing. So, before starting to make our RAM energy efficient, we went through some of other research works, or say we did a literature survey and found out that there are multiple ways for minimization or optimization of RAMs suitable for respective required applications or functions. Here are the references and ideas from other works that influence us to do our research. In our research, implementation begins by using FPGA-based RAM on Spartan 6 FPGA. As told earlier, operating frequency of a device is 1 GHz. The aim is to reduce power consumption so as to maximize utilization of our RAM. The total power consumption constitutes of clock power, logic power, signal power, input-output power, and leakage power consumption. It is also checked at different output load capacitance, which has also shown variations in consumption of power at different temperatures because we can't be physically present all around the world to test it. So we tested at coldest temperature recorded in Toronto and hottest in Texas. So we recorded our observation first using LVCMOS 25, that is VCCO, or input output voltage is set at 2.5 volts. We kept increasing our output load capacitance until the device becomes unstable, and we found out that the thermal stability is intact at maximum of 1000 picofarad. Observation table shows that the logic power consumption is nil at minimum of 5 picofarad and even maximum of 1000 picofarad. And also testing it at 50 and 500 picofarad, the logic power consumption is still zero and no change is observable in signal power loss where the value is 0.001. The most power consumption is visible in input out power consumption with increasing capacitance value, and so does the total power consumption increases. By plotting these values against a bar graph, we found out that total power reduces as we reduce the capacitance value. Also, lesser the temperature, lesser is the leakage power. There is about 84% reduction in leakage power as we move from 48.9 degrees Celsius to minus 33 degrees Celsius, and keeping the output load capacitance maximum, that is at 1000 picofarad. Now we test FPGA in LVCMOS 15, that is VCCO is kept 1.5 volts on 1 GHz operating frequency. Also at the temperature of 25 degrees Celsius. The table clearly shows that the clock power, logic power and signal power consumption remains the same at different output load capacitance value, but at a normal room temperature. The leakage power increases as the capacitance value increases. Therefore, to get lower power consumption, the capacitance value should be low. Also testing it at different peak temperatures, the graph shows that the lower capacitance value, lower is the leakage power. In different temperature scenarios, also the leakage power at hottest temperature is still lower than observed at the coldest temperature. Observation of LVCMOS 18 is also recorded at temperature of 25 degrees Celsius, that is a normal room temperature, and by LVCMOS 18 we meant that VCCO is at 1.8 volts. It is clear that as we change LVCMOS 25 and LVCMOS 15 to LVCMOS 18, as the capacitance reduces, the total power consumption reduces. Also, comparing LVCMOS 15 and LVCMOS 25, total power consumption is lower in LVCMOS 15. That is, the total power of 0.047 watts is recorded at 5 picofarad and is also minimum among all. Coming to the conclusion, we tested LVCMOS based RAM at different capacitance value of 5 picofarad, 50 picofarad, 500 picofarad, and 1000 picofarad, and got different results at different temperatures. As seen at 25 degrees Celsius, we found that there is overall power reduction of 32.85% in LVCMOS 25 compared to LVCMOS 15 with 5 picofarad capacitance value. So as we said, the capacitance at 50 picofarad, there is a power reduction of 48.90%, and at 500 picofarad, it is 61.54%. Hence, lower the temperature, lower is the leakage power. Also, with lesser capacitance along with the low temperature, there is total power reduction. It can also be tested under different circumstances using different softwares or even a version of Spartan or other series like Artex, Vertex. Since future is unpredictable, so is the change, and testing could be done in future in different aspects, in different scenarios. Thank you so much.